Ok. Acho que talvez a gente pode começar.
Sim.
Aliás, eu não sei se você prefere em inglês ou em português.
Para mim, tanto faz, vocês escolhem. Para mim, as slides estão em inglês, mas vocês escolhem. Para mim, tanto faz.
So I think we can switch to English. Yes. Okay. So I'll just a brief introduction of Professor Rogério. Professor Rogério Rosenfeld had his undergrad and master degree from Universidade de São Paulo. He had his PhD at the University of Chicago. Besides being a professor at IFT working in the areas of phenomenology, of elementary particles and cosmology, he is currently the president of Sociedade Brasileira de Física, also president of União de Físicos de Países da Língua Portuguesa, vice director of ICTP, South American Institute for Fundamental Research, vice coordinator of ENCT do E-Universo. He's a member of Laboratório Interinstitucional de Astronomia, linha, a member of the Dark Energy Survey, and a member of Rubin Observatory Legacy Survey of Space and Time. He is also the author of 2 books, Feynman and E. Gelman, Luiz Clarke's Ação and O Cerne da Matéria. So we are very proud to have Professor Rogério here, and I think you may have the floor, and you may start.
Okay, so thank you very much for the invitation to talk to you. It's always a pleasure to give a talk. Hope you enjoy. Yeah, so this little Congress, Congress theme, has a long history, and it's really good to see that you guys are carrying on this tradition of the Institute of Theoretical Physics. So congratulations for this initiative. So I will start sharing my screen to give a talk. So you're probably seeing my screen. So I apologize because I gave the same talk yesterday, and I'm just going to use the same slides. So I gave this talk at the colloquium at the Federal University in Rio. And the title, so first of all, the background here that you see in this slide is actually a picture of the dome of the telescope called the Blanco telescope, where the Dark Energy Survey camera is installed. So I'm going to talk a lot about the Dark Energy Survey collaboration and the results that we have. So this is a telescope in Chile, and I'm going to talk a lot more about that. So and also, so I'm a member of IFT-UNESP, ICTP Safer, Linha, and this Instituto Nacional de Ciência e Tecnologia. And the title of the talk, you may be curious to about the origin of the title. So if the universe is the answer, what is the question? So that's a very intriguing title. And in fact, I have a story about this because I was going to give a talk in 2018 in a symposium in Peru. And I thought about this title, exactly this title. I thought, wow, this is a great title, really, fantastic. And I put this title in the talk. But then before giving the talk, I started to think, wait a second, I think I saw this somewhere. And where did I see this before? And then I remember where I saw exactly this title, this question. And this is in this book that you may know or may not know. And this is the book called The God Particle. This was before the discovery of the Higgs. It's a very unfortunate title, not the God Particle, but there's a reason why it's the God Particle. The reason is that, according to Leon Lederman, the author of the book, the reason is that he wanted to call the Higgs boson the goddamn particle, but the editor didn't want him to call it the goddamn particle, so he decided to call it the God particle. But the subtitle of this book is exactly the title of this talk. So now I remember that I copied it from Leon Lederman. And it's very appropriate. First of all, Leon Lederman is one of the greatest physicists of the last 100 years, I would say. No? And so it's appropriate that I stole this title from his book, and I tell you why. So Leon Lederman, he actually died a couple of years ago. He won the Nobel Prize in 1988 for he was one of the co-discoverers of the muon neutrino. He was an experimentalist. And he was the director of a laboratory in the United States, near Chicago, actually, where I did my PhD, called the Fermilab. And in 1983, he had a vision to start a group in a laboratory that's particle physics, no? Experimental theoretical particle physics. They had a theoretical particle physics group. But he had a vision to start a group in theoretical astrophysics and cosmology. And this group started in 1983, and this was exactly the time when particle physics and cosmology were getting together and trying to put a coherent picture of the universe. So he had this vision, amazing vision, to start this group. And this is the group that led to the development of experiments that are not based, but are led by Fermilab scientists and Fermilab administration. And those are experiments in cosmology that really changed the landscape of cosmology. So this Low and Digital Sky Survey is a fantastic experiment that was, still is, taking spectra of galaxies and in fact, the latest data was just released this year. It's called the EBOS now, but it's basically this Low and Digital Sky Survey. And this was developed at Fermilab. And also the Dark Energy Survey is managed by Fermilab. The camera was developed at Fermilab. So it's very appropriate that they stole this title from his book, because I work in Dark Energy Survey now, and it's led by Fermilab, and this is all because of Leon Lederman. So the plan. Another thing I want to say. Please interrupt me at any time, of course. No, I know this is the last talk. You're tired, so I plan to be easy on you guys. So the plan of the talk, first a brief introduction, then I will describe how do we get the answers from observations, and then talk a little bit about the physics of perturbations in the universe, something that we use to characterize the fluctuations in the universe called the power spectrum. Then I will concentrate on the observations, the Dark Energy Survey, some highlights of the results from Dark Energy Survey, some challenges, talk about the future experiments like the LSST, and finalize. So answering the title, what is the question? The universe is the answer. So what is the question? The question is, what is the best model that describes our universe? That's what we want to know. And this is the main goal of this endeavor. And you have to know that models, as you probably know, models always depend on parameters. And what we do is that we analyze different models and compare it with data. And in the end, we provide probability distributions for the parameters given the data, given some measurements. And I hope to, at the end of this talk, you will understand how we do that. So before doing that, I want to just mention that modern cosmology, as we know today, is based on 3 unexpected discoveries. The first one is that there's more matter on galaxies and clusters of galaxies than what was originally expected from the light. And this gave the origin of dark matter. That gravity becomes repulsive on very large scales. This was a totally unexpected discovery, and this is the origin of what we call dark energy. And also that the universe was very, very homogeneous and isotropic, close to the Big Bang, 300,000 years after the Big Bang. We are 14 billion years. And this gave rise to a mechanism for explaining this homogeneity and isotropy called inflation. So the universe, modern cosmology is based on dark matter, dark energy, and inflation. And today we do have a standard cosmological model, which we call lambda CDM. And this model is based on the theory of general relativity, plus a cosmological constant, which is a model for dark energy. plus, of course, the non-elementary particles of the standard model of particle physics, plus cold dark matter, because in the standard model of particle physics, there is no candidate for cold dark matter, plus inflation. So this is the ingredients of the standard model, the standard cosmological model. And the standard cosmological model explains all the cosmological observations up to now. Beware of some recent tensions, especially in the measurement of the Hubble constant, which I can mention afterwards. So it explains everything we observe up to now. But we know that we do not know what 95% of the universe is made of. So it's important that we know that we don't know, because before we didn't know that we didn't know. Now we know that we don't know. There's a difference, a big difference. So as I said, almost 70% of the universe today is in the form of dark energy, which in the standard cosmological model is a cosmological constant. 25% in the form of cold dark matter, and only 5% of the universe today is in the form of atoms, things that we are made of, and very small percentage of photons, etc. No? I just want to call your attention that this picture here evolves with time. So when you go in the past of the universe, when you go back in time, this picture changes, and in fact, dark energy becomes irrelevant very soon. And the dominant part in the early history of the universe, the dominant component is actually radiation. So it changes photons and neutrinos. It changes a lot, this picture. So this is the picture today. So we don't know what's dark matter. It could be cold, it could be warm, it could be fuzzy. We don't know how it self-interacts or not. We have no idea what is dark energy. And as I said, the simplest model, which is the standard model, is a cosmological constant. But it can be a new degree of freedom, modified gravity. There are many, many models that try to explain or try to give another explanation for dark energy. And we don't know what drove inflation. There are very simple models with a scalar field that we call inflaton, but we don't know. And also it's important to mention that inflation gives rise to primordial gravitational waves that can be in principle indirectly detected. And you're probably going to see many of these figures representing the evolution of the universe. So the universe has a history that's important to emphasize. We know that the universe is expanding. So the universe today is different from the universe in the past, and it's going to be different from the universe in the future. And this figure is intended to give an idea of this expansion. And here you can see energies and times, because the universe in the early universe was in thermal bag, was thermal equilibrium, so you can talk about temperatures and energy. And you see that today we have galaxies and people and solar systems, and us, etc. Still a few particles, neutrinos, photons, etc. But if you go back in time, there were no galaxies, for instance, right? If you go back in time. So structure formation happens here when the universe was about 1 billion years old. But here, when the universe was 300,000 years, there was absolutely no galaxies. And this is the time when the cosmic microwave background radiation was generated. And if you go back, there were no atoms, because the temperature was so high that elements were ionized. So there were some nucleus of light elements and particles. And if you go even back in time, there were no nucleus, only nucleons, like protons and neutrons, but no nucleus. So this is a part where we call nucleus synthesis, where some light nuclei like helium was created, and this is about 100 seconds. So there was a very famous book, which I actually recommend a lot. It's called The First 3 Minutes by Steven Weinberg. It's a popular book about cosmology, which I read when I was in high school. And it's about this first 100 seconds of the universe when nuclear elements, light nuclear elements were formed. So this is a standard picture of the evolution of the universe. There was an inflation happened at the very, very first instance of the universe. We don't have any, how to say, firm evidence for the existence of inflation yet, but we all believe that inflation occurred because it explains many things. And inflation is a period of exponential expansion of the universe, so very fast expansion. And this is the same kind of thing that we're seeing today. Universe is expanding exponentially today also. So we're entering a phase of exponential expansion. So it's important to notice that the universe passes through many different phases. And it's like phase transitions in water, if you want, depending on the temperature of the universe. So this is a typical figure. I just can't resist showing another figure that I found recently. Is by an artist called Angela Gonzalez. And this artist, that's a picture of her, she died in 2015. But she was one of the first employees at this laboratory that I mentioned before, Fermilab, and she was hired to give all the how to say she was hired to make all the identity, the visual identity of the laboratory. She was an artist. And I really recommend to see this exhibit of her posters. And so everything at Fermilab, all the science and everything was her work, basically. And this is a great picture of the evolution of the universe, because it's not this simple linear thing. You know, this goes like opening up from quantum gravity, granification, matter domination until today. It's amazing. I think she's a genius. She's really a genius. Anyways, I love this picture. Maybe just show this from now on. So particle physics and cosmology are married by Einstein equation. So this is Einstein equation I wrote here. So the left-hand side is a description of geometry of the universe. So you give me the metric and I calculate, and the cosmological constant, and I calculate everything about the geometry of the universe. On the right-hand side, you have the energy momentum tensor, which is related to the matter, energy, pressure, content, which is given by particle physics. So when we talk about cosmology, we have to talk about general relativity and particle physics. So the standard model of particle physics works fine, but as you know, it's not satisfactory. So we don't know the origin of neutrino masses. Dark matter is not in the standard model. There's something called the hierarchy problem, which you may or may not have heard about. So phenomenologists are looking for physics beyond the standard model. And in the same way, the standard model of cosmology, which is called lambda CDM, so lambda cosmological constant plus cold dark matter, it works fine, explains everything so far, but it's not really satisfactory because, again, we don't know what's dark matter, we don't know what's dark energy, so there are many models that go beyond the simple lambda CDM. So there are many models. So how do we decide if the model is correct or not? We don't decide, nature decides. So we have to see what nature has chosen. And cosmology, it's amazing, it's a science, it has become a data-driven science, precision science. So when I started to study cosmology, I was a young kid, the age of the universe used to be written as 10 to the 9 plus or minus 1 year. So the error in the age of the universe was the exponent. And today, thanks especially because of the precise measurements of the cosmic microwave background, we have a very precise number for the age of the universe. 14 billion years was a very small error. So many probes, many observations are used to extract information about cosmology. And I have to say that one person really stands out in decades of work that he did to turn cosmology into precision physics, give a solid basis to cosmology. This person is James Peebles. And of course, you know that he was given the Nobel Prize in Physics, half of Nobel Prize in Physics in 2019, last year, for theoretical discoveries in physical cosmology, and it's really well deserved. So some of the cosmological probes that we analyze, as I already mentioned, the cosmic microwave background. I already briefly mentioned the synthesis of light elements in the early universe, so this is called Big Bang nucleosynthesis. And also more recent, there are studies of supernova of a certain type that are standard candles in the universe, or can be made standard candles in the universe. Gravitational lensing, distribution of galaxies, including something called baryon acoustic oscillations, which I will describe a little later, and number counts of galaxies. So in this talk, I'm going to concentrate on what we're doing, which is large surveys of galaxies, which actually refers to these 4 observables. So it's a good time to stop for questions before going further. And I saw many things on the chat. I'm not sure if there are questions or not.
Yeah,
I cannot read the chat right now.
Julia has a question. Do you want to open your mic?
I was in doubt about the structure, but I I didn't know if I interrupted you or not. So, but I was in doubt about what is the structure formation. Like, I always see this image, and then I don't know really about this structure. So I don't know if you can explain a little bit to me.
Yes. I will talk more about this, but the idea is the following. The idea, if you go back and see here, the universe here, when it was 300,000 years old from the Big Bang, it was very, very homogeneous and isotropic. And there were no galaxies here. This is something that you have to think about. I say some more things about this, but there were very tiny perturbations. And these tiny perturbations, they evolved with time because of gravity, and they give rise to structures. And when I say structures, maybe you don't know what I mean by structures, but I really mean the formation of galaxies and clusters of galaxies. And there are many ways of studying this. But in fact, when you go to the real problem of formation of structure, you cannot use analytical tools anymore because the fluctuations are not small, they're very large. So what people use are simulations. So they take a distribution of very homogeneous distribution of point particles, let's say, and just let it evolve with time. When you do this, you start to see this formation of filaments, structures really, and more sophisticated simulations that include baryons, no gas. Then you can really see galaxies forming, and that's amazing. The simulations are very sophisticated, and you can, if I have time, I don't have it here, but we can look in the internet. There's several of these simulations. One very famous is the Millennium simulation, but now there are many more simulations that are much more sophisticated than the Millennium. So, so when I say structure formation, I mean to get from these small perturbations where there's no galaxies, no planets, no nothing, right? It's only a diffuse plasma and with small perturbations, and they grow with time and they form galaxies. And that's galaxies, clusters of galaxies, and this web. So when you look at the distributions of galaxies, you see a web of galaxies and clusters of galaxies. So it's a very rich distribution. And what we do is actually we analyze this distribution of galaxies statistically. That's what we do. So thanks for the question. And if I probably touch upon this later on again. Okay,
thanks.
Okay. More questions?
We have one more question from Rubin. Do you want to open your mic or do I read it? So I think I'll read the question. Would you know if there is any progress in the so-called quantum gravitation? For example, in the Sakurai book shows that gravity is not purely geometric at the quantum level as a consequence of the so-called gravity-induced quantum interference.
Right. So you can say that gravity, you can estimate when gravity needs to be quantized, let's say, no? And this is at a scale called the Planck mass. I'm not sure if you heard about this scale. It's called the Planck scale. The Planck scale is, you can compute from Planck constant, basically. And it's given by 10 to the 18, well, and Newton's constant. And it's given by, it's in units of energy, which is the units I'm used to, is 10 to the 18 giga-electron volt, GeV. If you put that in terms of degrees Kelvin, it's like 10 to the 32. So it's really an epoch in the universe, very, very early on, where we do not have access to it observationally yet. Okay, so quantum gravity at this point is a theoretical speculation, I would say, because there's no evidence yet of no probe that we can check what happened here yet. Now, I have to say, however, that quantum effects are important in the universe, especially during inflation. And in the inflationary phase of the universe, quantum fluctuations, not in gravity, but in a scalar field, is responsible for the origin of these very tiny fluctuations that we think is the origin. Again, there's no direct evidence. But at least we know how to compute semi-classically. And we think it's the origin of the perturbations that actually gave rise to galaxies on us in the end. But quantum gravity is different, right? So we don't have a complete theory of quantum gravity, and we don't have direct evidence of this phase here of the universe. But this is, look, this is 10 to the minus 43 seconds, right? So I would say that we know the physics pretty much from the electroweak epoch to today, because that's where we know the physics. Granularification, we don't know if granularification existed or not. And we believe there was cosmic inflation, but we don't know exactly when cosmic inflation happened. So I would say, if you want to be very conservative and use the physics that we know and have tested in laboratories, we would describe the universe from the electroweak epoch on. I hope I answered the question. More questions?
So Rubin, thank very much for your explanation. Also, just a reminder, you have 15 more or less, between 10 and 15 minutes left.
Oh, 10 or 15 minutes left for the talk?
Yes.
I have to finish in 10 or 15 minutes, is that right? Okay.
More or less so.
I can do it. I can finish whenever you want. Don't worry about it. Okay, so I want to say a few things how to get from observations to answers. So the main goal is to find out what is the best model that describes our universe. And you can think of easy steps. If first you choose your model, you choose your observational probe, you compute predictions from the model about the probe, for a given set of parameters. Then you find some data, compare model predictions with data, and find the best model with the corresponding values of the parameters. So it seems pretty easy, and you can put all the steps together in something we call the likelihood function, which has to do with theoretical predictions, which depends on parameters, observations, something called the covariance matrix, which gives you the uncertainty in the experimental measurements. And all you have to do is to maximize and find the best parameters. So it sounds very easy, and it's not very easy. First of all, theoretical predictions are very difficult because you have nonlinear physics, you have astrophysics that you have to take into account, like, what's the effect of supernova explosions in the formation of structures, etc. The measurements are difficult, there are errors in many of the measurements. The estimation of the covariance matrix is difficult. We don't know if this likelihood is Gaussian, how to take account prior information about the parameters, and how to actually estimate the parameters. You have many parameters, and what you have to do it in a Monte Carlo way. So we have to run what is called Markov, Monte Carlo Markov chains. And then what we want to be precise and accurate. So we don't want to be precise and inaccurate. So it's a big responsibility to have an idea, a very good control of the systematic errors to be precise and to be accurate. Okay, so I don't think, I have 10 minutes, right? So I will skip everything.
Actually,
Professor,
I think you
we
can,
start a little bit late. Okay,
yeah, you can have a little bit more.
Yes,
so
and everyone, the chat
yes.
is actually asking for more. So you
Yeah,
can have
so
like
it's the last.
20,
It's the last.
yes, you can have at the time that you think it's okay for your presentation. It's fine. Everyone in the chat is asking for more. So
Okay, so is half an hour too much?
no, it's okay. It's okay.
Fine, yeah.
So I try to finish in 20 or 20, let's say 20 minutes, okay? So I talk about perturbations in the universe. Let's see what, yeah. So as I mentioned briefly, that inflation, this process that we call inflation, generated, it's amazing, this story, because when inflation was postulated, people didn't know that it could actually generate small density perturbations. It was afterwards that they did. But inflation, the inflationary models that we have can generate these small density perturbations in the universe. Because I just want to say that suppose this is funny, you know. So people discovered the cosmic microwave background. So they found this thing that was completely homogeneous and isotropic when they couldn't see differences. They point to one part of the sky, they see one temperature. They point at the other part of the sky, they see exactly the same background temperature. So before 1991, there was no evidence that there was any departure from homogeneity and isotropy. So can you imagine what would happen to the universe if there were no inhomogeneities, everything was homogeneous and isotropic at the time of this cosmic microwave background generation? Can you imagine what would happen? I can tell you, we would not be here because we are the product of the evolution of these small perturbations. So it's great that, well, first of all, they were measured, and then but they are also predicted by inflation. So, so these perturbations are very small, but they grew with gravity and originated the structures that we observe now. And just to give a number, of how small this tiny perturbations are, very small. They're 1 part in 100,000. So this delta here is what we call density contrast. It measures exactly the variation of the density with respect to an average density. So that's the evidence that the universe was extremely homogeneous and isotropic. So at the level of inhomogeneities was this 1 part in 100,000. And the discovery of these fluctuations led to a Nobel Prize in 2006. Now, these small perturbations, they evolve and they form galaxies. And this is a very difficult theoretical problem. That's one of the reasons of the challenges to test models, because you need models to connect these very small perturbations to galaxies. But it's a beautiful story because it starts from quantum fluctuations produced during inflation in a scalar field to generation of the cosmic microwave background to the formation of galaxies. It's fantastic. And another challenge that we have is that we don't observe matter directly because, as I said, most of the matter is dark. So baryons are we only observe galaxies, so we observe light. So we don't observe dark matter when we look at galaxies directly, no? So, so there's a bias between the galaxies that we observe and what is the dark matter behind them, right? And this is a parameter B we call bias, and we don't have a good model for bias actually. And this what is important to emphasize is when you have a model, the model is for density perturbations in matter. And the observations are in galaxies, and you have to translate this, and this is using this bias. And we don't have a good model for that. Again, we have to rely on simulations or some simple models. This figure here just illustrates, if you want to see where most matter is not where most light is in the planet Earth, for instance. And again, another illustration that shows the evolution of very small perturbations through gravity to form structures, these galaxies that we observe. So the evolution of perturbations are difficult to compute. In principle, it's not possible to compute analytically because general relativity is non-linear, and there's no way to make expansions if the perturbation is large. So there are large numerical simulations that were done, mostly using Newtonian physics. You don't need GR for this. And sometimes only cold dark matter is considered, and that's easier simulations, but also more sophisticated simulations now take into account barriers. But linear perturbations are easier to compute. And linear perturbations are the ones that you need up to here, more or less, okay, when the perturbations are small. And again, just to remind you that when the universe was 300,000 years old, the perturbation was very small. And the number that I like to remember is that the average density today, after 14 billion years of the universe, so this is a number that's, it's mind-boggling. The average density of the universe today, this is something amazing, corresponds to 1 proton per cubic meter. Can you believe that? So this is, and we measure that this is the average density of the universe today, which is called the critical density, by the way. So we know that the universe is spatially flat. So we are at the critical density, we call it critical density. And the critical density is 1 proton per cubic meter, more or less, of this order. So you can imagine that we're very, very large fluctuations over this average density, right? So here, the perturbations are very small, 10 to the minus 5. But now, the perturbations are huge because the average density was 1 proton per cubic meter, but the density here in this room is, I don't know, 10 to the 23 protons or whatever. So it's huge. So we're very large fluctuations in the universe. So again, perturbations evolved to form galaxies, and the distribution of galaxies in the universe and tiny distortions in the shapes of the galaxies, they provide important tests of cosmological models. And we characterize these distributions by correlation functions, which I'm going to talk about, or the correspondence in Fourier space. So we can analyze things either in real space or in Fourier space. And in Fourier space, the correlation functions are called power spectrum. So maybe you heard about this word power spectrum, and the power spectrum is nothing else than the Fourier transform of correlation function. So what is a correlation function? So first of all, I wrote this several times, but the fluctuations can be characterized or described by this density contrast, which is just the density at one point minus the average with respect to the average. And if we can characterize it by its moments. You can think of this as being a random variable, but the average, so is the first moment, 1 point correlation function is 0 by construction because the average of the row is rho bar, so this is 0. And then you can do a 2-point correlation function, which is called the variance. And by homogeneity and isotropy, this only depends on the distance between these 2 points, x1 and x2. And the interpretation is that this is just a excess or deficit in the probability of finding galaxies separated by a distance r over a random distribution. So this C here of R is called the correlation function. And the Fourier transform of this correlation function is called the power spectrum. And you can work in both cases. You see that we're working mostly with power spectrum. But the interesting thing to notice is that if you have a very sharp feature in the correlation function, a very characteristic distance, for instance, it translates in the power spectrum in oscillations. So the baryon acoustic oscillations is nothing more than one specific scale, which is the baryon acoustic scale. And interestingly enough, there is a preferred scale for galaxy distributions, and this is baryon acoustic oscillations. This is given by physics. This is the scale where the atoms are formed in the universe, and the light decouples from matter. And this has been detected, in fact, in 2005. This is amazing. And this power spectrum also is sensitive to new physics. So for instance, this is a plot of the power spectrum as a function of k here for different models of dark matter. And this is the linear power spectrum for different masses of dark matter. And you see that there's a suppression of the power spectrum, the lighter the dark matter particle is. And in fact, this is the reason why dark matter cannot be neutrinos, because it will be a suppression in the power spectrum that we don't observe. Now, this is true at the linear level, but if you do non-linear level, then things are much more complicated. And this is just a work that I did with my student Jessica Martins and Flávia Sobrera about the how to take into account non-linearities. And then the situation becomes much more difficult to distinguish between different dark matter masses. And also distributions of matter in the universe affects the shapes of galaxies, and this is called weak gravitational lensing, and that's illustrated in this figure. So if you take a look at these galaxies in the background here, and we look at these galaxies today in our telescopes, and suppose the light has to go through some large amount of mass, this light is distorted just by general relativity effects. And what you see is that the shapes of these galaxies here, which are, they look random here, now they do not look random. I don't know if you can see this, but they're kind of a line here, and they have this pattern. And this is called weak gravitational lensing. This is just one picture, but this is not weak. This is really strong. We're looking at much smaller effects in the distortions of the shapes of the galaxies, and this gives information of all the matter between us and this distant galaxies. So, and the so-called two-point correlation functions, they contain a lot of information. They actually contain all the information for Gaussian random fields. So what we measure in dark energy survey, for instance, are these two-point correlation functions. And in fact, we measure the correlation functions of the positions of galaxies, of the shapes of galaxies, and the cross-correlation between positions and shapes. And the jargon name we give, if you are in the field, is called 3 times 2-point data, because there are 3 two-point correlation functions, right? And this is called 3 times 2-point. So now I'm going to talk about the dark energy survey a little bit more. So there are many large-scale galaxy surveys. Some already took data, some are taking data. And I'm going to concentrate on the dark energy survey, but our group also works in the dark energy spectroscopic instrument and the LSST. So the dark energy collaboration is an international collaboration. It's led by Fermilab. So the first director of the collaboration was John Peoples, who was a former director of Fermilab. Second was Josh Freeman, and the third is Richard Crum. It's a collaboration of, I think, more than 300 now. And Brazil is part of this collaboration. And the Brazilian participation is through this Linea laboratory, and also we are financed by the this project INCT of the E-Universe. This is just the homepage of Linea, just to show that it gives support to these experiments here, and we have lots of activities like webinars and stuff. And the dark energy survey science summary, what we want to do is to use galaxy clusters, weak lensing, baryon-acoustic oscillations, and supernova to constrain models of the universe. And one model of dark energy, for instance, can be given by what we call an equation of state. An equation of state is just a relation between pressure of dark energy and density of dark energy. If it's a cosmological constant, in this parameterization, W0 would be -1 and WA would be 0. So if you look here, this is just a forecast. So the fiducial value is the cosmological constant. So this is centered in -1 and 0. But what you have to look at is the precision that we have access to, and also that the combination of different observables makes a big difference in constraining these models. So this is very important. And just a few things about the dark energy survey project is that it covers 1/8 of the sky. We already have 300 million galaxies in our catalogs. 300 million galaxies. This is a lot of galaxies, up to redshifts of 1.2, 1.3, plus 100,000 clusters of galaxies and several thousand supernovas. We don't measure the redshift with spectrum, but we use another technique called the photometric redshift. So we take pictures with 5 filters, and it's much less precise than spectroscopic redshift. But however, we can have many more objects and use this telescope in Chile, the Blanco telescope, is a 4-meter telescope, and a digital camera with 570 megapixels. Just to have an idea of how long it takes a project like this. So the construction of the camera started in 2004. Sorry, the research and development started in 2004. The construction started in 2008. And the first light in the telescope was 2012. So you can see 8 years just to get the first light, and then 5 years of observations, or 7 years of observation, 6 years of observations. So the experiment is finished. We took all the data. Now we need to analyze the data. So this is a picture of the telescope here. It's in La Serena, near La Serena in Chile. CTIO, Cerro do Bolo International Observatory. This is a picture of the telescope with the camera on the focal plane. So this camera weighs 4 tons, and it takes pictures that can have 100,000 galaxies up to 8 billion light years away, each picture. And this is the CCD array. This is a picture in the CCDs, just an idea of the resolution. This is how the moon would look like in our camera, just to have an idea of the coverage of the camera. And again, distribution of galaxies is going to give you lots of information. Each picture takes 500 megabytes, and so we have 150 gigabytes per night, which is transferred to a center in Urbana for processing. And we have contributed to software and the science portal. This is the footprint. I will not have time to go to this, but we have to take pictures in different filters, so those are the different filters. And this is for DES year 3. We already finished DES, so but we're analyzing the year 3 data right now. And as I said, the redshift measurements are done using photometry, so they're not very precise. So we divide the survey into redshift beams, and we do our measurements tomographically. So we project our measurements in redshift beams. So a number of results were already obtained. I will highlight some results from the year 1 analysis, because year 3 is still in progress. It should be done in 1-2 weeks tops. And we did some work on bioacoustic oscillations in harmonic space. And the main results of DES year 1 is one combining the 3 times 2 point function of the galaxy clustering and weak lensing. And we are continuing working on year 1, our group in harmonic space for the whole power spectrum. So there were, last time I counted, there were 280 papers of the year 1, many results. There was I won't go into this, but I just want to mention that we found the optical counterpart of a gravitational wave event of neutron star fusion, which was led by Brazilian Marcelo Soares Santos. So our DS team, past and present, we have the postdocs Felipe Andrade Oliveira, Hugo Camacho, Fabian Lacasa, he already left. He got another postdoc in the University of Geneva, and he's now in Paris. Antonino Troia just finished his postdoc, he's back in Italy. We had as students Nico Kron, he finished, and he's a PhD student in Stanford. Andresa Campos finished her master, she's now a PhD student in Carnegie Mellon with Scott Donaldson. Otávio Alves is about to finish, but he already started his PhD at the University of Michigan with Dragan Hutterer. Maria Gabriela Cota is about to finish. Lucas Faga is a student of Marcos Lima. And João Rebouças and Diogo Henrique, they are starting in our group now. And we also work closely with Flávio Sobreira, professor at Unicamp, Marcos Lima, professor at USP, Vivian Miranda, senior research at Arizona, University of Arizona. So I really want to finish, so I will skip this. So this is a paper looking at the baryon-acoustic oscillations in the angular power spectrum, and this was led by Hugo Camacho and Nico Kron. So this was led by our group. So we estimated the baryon-acoustic oscillation scale. I won't go into details, but we are able to contribute to this result here, where we put a point in something that is similar to what's called the Hubble diagram for dark energy survey. And the main analysis, which we also contributed, uses 2 types of galaxies, 2 types of catalogs. One is the shape catalog. Remember, we want to study correlation of shapes, and you also want to study correlation of position. So there's a shape catalog and a position catalog, and you have to work with them, with these catalogs. These are just to have an idea how many parameters we have to actually consider in the analysis. So that's why we have to run expensive Markov, Monte Carlo Markov chains. And we contribute here for the study of the covariance matrix for the year one, something that's kind of complicated. But I just want to show the results, and this is the results considering only two observables. One that's related to the fluctuations at a given scale of perturbations today, and another is a quantity related to the amount of matter in the universe. And I just want to show this because it compares results from the dark energy survey, only the year one data. So this is the blue region with the Planck satellite from CMB. So these are results that are totally independent. And one actually gets their data from when the universe was only 300,000 years old. And our data is when the universe was 14 billion years old. So it's amazing that the data are compatible, and also that they are the same order of uncertainties. This is the first time that a galaxy survey has uncertainties which are of the same order as a CMB data, which is amazing. And the red area is the combination. We can combine both of them. And this is a test of another model where the cosmological constant is not constant. It's not a cosmological constant, but it can have a different equation of state, but a constant equation of state. And again, we confirm that it's something very similar to the cosmological constant. Now, this is some work that we are doing in our group in São Paulo. We are studying galaxy clustering harmonic space, again for year one, and we show that they're compatible with results in real space. So this is the first step, and the idea is to redo the whole year one analysis in harmonic space, but also do the harmonic analysis in the year three. So in year three, the data from the first 3 years, there's 5 times more data. There are 300 million galaxies now. We are leading the baryon acoustic oscillation paper in harmonic space, and we're having a major role in the covariance validation paper. This is just a plot from the covariance validation paper that we finished, actually. We finished this yesterday, and it's going to be internal reviewers of the collaboration. This is just one plot to show all the details that we tested when we propose a model for the covariance matrix. And I want to talk about the future in 2 minutes now. The future, of course, as I said, dark energy survey has finished taking data, but of course we're still working on the data analysis. But the future is the Rubin Observatory Legacy Survey of Space and Time, LSST, which will start taking data in 2022, and will take data for 10 years. And Brazil has 10 principal investigators in this project. This is an actual picture of the construction site. It's a brand new telescope, 8 meters. We have the largest digital camera ever, and it will be an amazing instrument. And it will do lots of stuff. It will cover the whole sky every 3 days, for instance. And in addition to studying dark matter and dark energy, we'll do lots of other stuff, especially transient phenomena. So we are members of the so-called Dark Energy Science Collaboration in LSST, and these are the members. So Mariana Pena Lima is a professor in Brasília, Valerio Marra is a professor in Espírito Santo, Marcos Lima USP, Sandro Vitente in Paraná. He's also a pipeline scientist. Felipe Andrade Oliveira, postdoc, is also a pipeline scientist. Lu Camacho, William Miranda is a pipeline scientist in the University of Arizona, and myself. And also, we are also participating in this spectroscopic instruments called dark energy spectroscopic instrument. And through negotiations, we also, in-kind contributions, which actually Felipe worked a lot in order to get these in-kind contributions. We have 2 PIs, and Flávia Sobreira from Unicamp is one of the PIs. And this instrument is already taking data. So to finish up, I hope to have convinced you that cosmology has become a precision and data-driven science, that cosmology tests models of fundamental physics. So what is dark matter? What is dark energy? Any discovery that dark energy, for instance, is not a cosmological constant would be revolutionary, probably a Nobel Prize. But we haven't found any evidence yet. There are new experiments that are taking data now, and many others are planned. So I've just mentioned DESI and LSST. So this LINEA and INCT provide opportunities for researchers to work in these cutting edge experiments. The computational infrastructure for these efforts must be improved, and there's a proposal to have a independent data access center, this IDAC, and that will increase the Brazilian participation in these experiments. The darkness survey analysis of year 1 data is mostly finished, and the papers from the analysis of the year 3 data is, they are getting ready in 1 or 2 weeks. So it's an exciting time, and let's hope for surprises. So thank you very much.
Well, thank you very much, Professor Rogério, for your talk. I think we already have someone who wants to make a question. Marcos Vinicius, are you there? Okay, go ahead. I think I can't hear you actually. Sorry. I think
Marcos,
I can't hear you. Marcos.
Your microphone is really low. We can hear you.
And now can you hear me?
It's a little bit better.
Okay, I'll increase it. Okay, I don't know if I can increase the volume more than this. Can you hear me? No. Can you hear me? No.
I can, but it's still a little bit low.
You can try. You can try. If you want
Yeah, go
to
ahead.
listen to you, then you go to the chat, okay?
Okay, let me try just one more thing. I don't know now. No. There's some difference.
I think.
Okay, I think
you can write your.
Yes.
All right.
Yeah, it's.
Actually, I'm reading the
And.
Okay. Maybe while Marcos is reading, then Bruno can do the question.
Bruno.
Okay, sorry. Hi, Professor Rogério. First of all, thanks for your lecture. It was very, very joyful. And I would like to ask you why is there no well-established physics below the Planck scale?
So what I call well-established physics is physics that's tested.
Okay.
We have not tested anything beyond the electroweak scale. So the largest energy scales that we have tested in laboratory is the, I would say, is the LHC scale, the Large Hadron Collider scale, which is about 1 tera electron volts, so 1,000 giga electron volts. So this is what I say is a solid knowledge, something that we are sure of. At higher energy scales, we don't know. We don't know what's there, really.
And do you know if we in the future we will be able to reach these energy scales with larger colliders or not?
No, not with colliders. But however, in cosmology, we can have information from these scales as well. So if we detect, let's say, primordial gravitational waves that were generated during inflation, we have a lot of information about the inflationary epoch that happened very, very early on. Not when gravity was needed to be quantized, but early on, okay? So we have lots of information. And in addition, we don't know if there were like grand unified theories. We don't know, we even don't know much about the electroweak phase transition or other phase transitions in the universe. And some phase transitions, as I said, the universe passes through different phases, no? So phase transitions can give rise to large fluctuations. And if it's a first order phase transition, you have bubbles like water, no? When it boils, it has bubbles that are formed. And when bubbles collide, they can produce gravitational waves as well. So there are many theoretical papers already saying or exploring the possibility of gravitational waves generated in first-order phase transitions in the universe that can, if detected, they can give you some information about those phase transitions. And again, if you detect some primordial gravitational waves, which are they are stochastic, but they can be detected indirectly. Then you can have some information about those early stages of the universe.
Okay, thanks.
So Marcus asked his question, Professor, how do you see the torsion-related gravity cosmological models?
Yeah, I'm not an expert in this torsion-related gravity cosmological models, so I really cannot say much. I just say that it's the right time to test models. So if you have a model, you have plenty of data to see if nature has chosen your model or not. So I would say take this model seriously and compute predictions for, let's say, the correlation functions of galaxies, and also the cosmic microwave background, and see if it agrees or not with experiments. So we have to be agnostic about these models. Have to test. You have to test models.
So we have another question from Anna Fogel. Professor, thank you very much for a great talk. Maybe this is a naive question, but the question is the following. In the picture, when you show the phases of evolution of the universe, why are we right now in an epoch where dark energy dominates? What exactly happened?
That's a great question, Anna. Thank you. So in fact, we don't know, and it's a coincidence. And we call it a cosmic coincidence. So I didn't say much about this, but I did say that picture, the pie diagram of the universe, that is 70% dark energy, etc. That is today. But if you go in the past, so I just give you an example, right? Take a gas of particles, non-relativistic particles. The density is proportional to the volume. If the particles are not created or destroyed, the density is just proportional to the volume. So if you decrease the volume, the density and the particle number is the same, the density increases inversely to the volume, right? So the density in particles, non-relativistic particles, increases as you go back in time because the volume is decreasing, and increases like the scale factor. So this typical scale of the universe to the power 3 because it goes like the volume. Now, the energy density related to the cosmological constant is a constant, does not vary with volume. So if you see, then there's a variation in the energy density of matter and also radiation. Radiation is even faster, and so it goes like this. If you're seeing my hand, and cosmological constant goes like that. So in the past, cosmological constant is totally relevant. But when you go to the future, it goes like that, and at some point, the cosmological constant starts to dominate. It's bigger than the energy density in radiation or in matter. And the values we measure, no? We measure the amount of dark energy, we measure the amount of dark matter, we measure the amount of photons. So we know exactly how things evolve, and you can compute, in fact, when at what time this dark energy starts to dominate, and you know, it's about billion years. That's the typical time. But why is that? We don't know, and that's called the coincidence problem. It depends, of course, on the value of the cosmological constant. So we don't have a good explanation for the value of the cosmological constant. By the way, you may know that we can think of the cosmological constant as a vacuum energy. And if you compute the contribution of the vacuum energy from just 0-point fluctuations, this contribution is divergent. It diverges like the cutoff to the 4th power, is a quartic divergence. So if you cut off the divergence at the, say, the Planck mass, because you don't trust this calculation with the Planck mass, you get this famous 120 orders of magnitude difference between the prediction and the measured value of the cosmological constant. So that's called the cosmological constant problem. So we don't have a, not only we don't have a good idea of the value, but if we try to compute from what we know from quantum field theory, from 0-point fluctuations of quantum fields, you get a value that's totally in total disagreement. It's the largest disagreement in measurements and predictions in physics.
We have more questions. We can actually go further if you have questions.
Yeah, so Marcos Vinicius, I really don't know much about the torsion. So I have no idea about torsion playing the role of dark matter, but yeah, the first thing you have to study these models and see if they can predict anything. If they can predict, I give an example, right? I would say that the most, or let's say the best motivated model for dark matter is from supersymmetric extensions of the standard model. So they predict a lightest supersymmetric particle, which is stable, and it may be neutral. In that case, it's a candidate for dark matter. And it has weak interactions, and you can compute. So it has some weak interactions. So in the early universe was in thermal equilibrium, and you can compute the abundance of these particles today, and it's of the order of what is expected. So if you have another model, you have to be able to compute the abundance and see whether or not it agrees what we measure.
I think Pedro Bita has his hand raised. Do you want to open your mic?
Yeah, since we have a little bit more time, I would like to ask a question. First of all, thank you, Professor. It was a great talk. In that picture you showed by Angela Gonzalez, there is a region in the electric epoch called the desert. So my question is, do you think that particle physics should become cosmologist if this is true? If there is really a desert and, well,
yes,
nothing shows up in the LHC?
So you know what the desert is, right?
Yeah, I suppose there is no more particles until grand unification and this thing.
Yes, yes. So we don't know. We don't know. The answer is we don't know, right?
Yeah.
It's a possibility that there is no new particles. We were guided. I don't know if you had a talk about the hierarchy problem in the standard model, but our naturalness. We were as particle physicists, we were guided by something called the naturalness principle, and that has to do with avoiding fine-tuning in nature. And this guiding principle would say that there should be, because of the Higgs mass, the protection of the Higgs mass, etc., there should be new physics at the scale of the LHC. And we did not find new physics at the scale of the LHC yet. So even supersymmetry was proposed exactly for that, to protect the Higgs mass from large quantum corrections and avoid a fine-tuning problem. But we didn't find supersymmetry. So there's no, I would say, that there's no guarantee that we'll find new particles at the LHC. And if you push me and say, okay, so let's build the next collider, 100 TeV colliders. If you really push me and say, do you guarantee that you'll find some new physics? I cannot honestly guarantee that there will be new physics. So it is a logical possibility that there will be a desert, okay, with no new particles discovered. If particle physics should turn cosmology, I don't know. Look at me. I was a particle physicist. But okay.
That's something I will keep in mind.
I will not answer that question.
Okay.
So, do we have more questions? Actually, I would, Julia has her hand raised, but actually, I would like to remind you all that you can also ask questions in Portuguese, in whatever language you feel.
Yeah, absolutely. I speak Portuguese.
So, Julia, I guess you had yes, go ahead if you may.
I don't know if you want to ask or it's okay if you want to ask. And I don't know if I ask in English or Portuguese, but I was thinking about the next structure that we discussed earlier. And I don't know why, but I am a little bit bothered with this idea, but it's maybe because I never really thought about it. So I don't know. I don't know if you can explain a little bit more, because I think I was thinking like there is this net and these conglomerates that it was that is this I don't know, galaxies, and like this structure is just in the simulations just this I don't know, it's a kind of how this came together, or it's really a structure, it's really a formation. I don't know if I defined my doubt, but I think I didn't understood well. I understand well the structure. I think it is this the problem, maybe, I don't know.
Okay, let's try to see simulations. Millennium simulator. There's a Millennium simulator. The best one now I think is Eagle. So let's see if there's a video.
Sorry, I know that this is very silly.
No, not at all. No.
I don't know. I never thought about it.
What you're asking, Julia. Very important. So hopefully this will explain. This is something that is started very homogeneous and is evolving with time.
Sorry, Professor, I think if you're showing something, we're only seeing your slide. Right.
Okay, so now you're seeing my screen?
Yes.
So it's a movie on YouTube. So let me go back here. So this is a simulation called Eagle simulation. You can go, and that's what I did. I just Googled Eagle because I knew the simulation. Mm-hmm. And this simulation starts, let me stop here for a second. So it starts at when the universe was 0.3 giga years, and that corresponds to 50, and this corresponds to a moving scale, or a scale of 25 megaparsecs, I think, if you can read this. And so this is a simulation and started very homogeneous, right? So there you can see, it looks like a cloud, right, Julia? You're seeing a cloud.
Yes. And
then this will evolve with time only through gravity, okay? Mm-hmm. So this is the evolution of intergalactic glass. So this is EAGLE stands for Evolution, Assembly of Galaxies and Their Environments. And this includes hadrons, which is much more difficult. I show another one that's easier, but let's go through this first. So what you see is a simulation, and you see that there are some filaments that are forming, right? Mm-hmm. And in these filaments, what are these things? They're over densities. They're things where the universe is denser here. And what you see now, you see that there are regions where these filaments intersect, and they're even more dense and more dense. And eventually, these things will give rise to galaxies in these simulations. Let's see. Probably we'll go through. So these are the simulations I'm talking about, and these are the structures I'm talking about that are forming. Mm-hmm. From this very uniform distribution of matter, evolves under the influence of gravity, and here it has gas, so it also dissipates, and forms structures.
Mm-hmm.
So this is what I mean by structures. And I want to show you, after this is finished, what we really measure, okay? So maybe if we go to slow and digital space survey. So this is movies, images. Yeah, this is an old one, but this is the actual distribution of galaxies. So each point, each dot here is a galaxy, okay?
Mm-hmm.
Sorry, is this plot here? Can you see my mouse?
Yes.
So this goes, this is a slice of sky, and you're going to higher redshifts, okay? And this goes only to 0.14, but it doesn't matter. And you see each point is a galaxy, and you see these structures in the universe, these filamentary structures that appears in the distribution of galaxies. Here, there's even what we call a wall of galaxies here.
Mm.
And then you can say, okay, but this is strange, right? Why the galaxies are not uniformly distributed? Well, because gravity is nonlinear, and furthermore, you have baryonic effects, so dissipation. So I want to show another simulation which I found easier for me to understand. Let's see videos. Well, okay, you can find videos of this one is probably okay. This is the most recent one. So this is the eBOS, and this is the 3D map of the universe from eBOS.
You are looking at the most detailed three-dimensional map of the universe known to humankind, and it's called the Sloan Digital Sky Survey. Scientists from around the world have just completed a 20-year-long survey of the night sky, measuring the positions and distances of more than 4 million galaxies and quasars. This detailed map will help scientists shed light on the remaining mysteries of the universe. Let's go on a journey from the local stars to the largest scales of our universe. Beyond the local stars that draw familiar constellations in the night sky in the neighborhood of the Earth, in addition to our own Milky Way, billions of galaxies are spread throughout the observable universe. Moving faster than light, we will take you through space in a journey from our place in the Milky Way all the way out to the large-scale structures of the visible universe, and we'll tell you about how we're mapping it out. Since 1998, the scientific community has realized that the universe is not only expanding, but its expansion is accelerating. This unexpected acceleration constitutes one of the major conundrums in physics. From a theoretical perspective, the acceleration may be accounted for by either assuming that there exists some mysterious dark energy, or by modifying Einstein's theory of gravity, called general relativity. In the same year, the Sloan Digital Sky Survey was launched to tackle this enigma of the accelerating expansion of the universe. The Sloan Digital Sky Survey is a vast collection of the angular positions of galaxies observed in the sky, as well as their distances from us, determined by observing the systematic shift of galactic light induced by the expansion of the universe, the so-called redshift. In this new map of our universe, the large dark patches are mostly regions obscured by the Milky Way that cannot be observed. During the last 20 years, through 4 exploratory phases, the Sloan Digital Sky Survey has created the most detailed 3-dimensional maps of the universe. To achieve this, it focused on different classes of galaxies, nearby galaxies, red galaxies, more distant star-forming galaxies, and superluminous distant active galaxies called quasars. The 4th and latest Sloan survey took place from 2014 till 2020. During this time, the new project called the Extended Baryon Oscillation Spectroscopic Survey, or eBOS for short, continued previous Sloan mapping of the extragalactic sky and just recently finished measuring distances for 1 million galaxies and quasars. These successive surveys allow scientists to trace the large-scale structures of the universe up to a fraction of its horizon, represented by the cosmic microwave background emission, seen here as a colorful pattern projected onto a sphere. The cosmic microwave background is the thermal relic of the universe, which dates back to about 400,000 years after the birth of the universe, also known as the Big Bang. Adding the EBOS data to the previous Sloan exploratory phases 1, 2, and 3, the Sloan Digital Sky Survey now has a database of 4 million galaxies and quasars, assembling the largest and most complete 3D map of the universe to date. This unprecedented achievement provides scientists with new tools for shedding light on dark energy and also for constraining the theory of general relativity, leading to a better understanding of the fundamental laws that rule our universe.
Legal esse vídeo, né? Então, esses são os dados mais recentes do Sloan Digital Sky Survey, na verdade agora o EBOS. Eles têm 1 milhão de galáxias. Eu falei que o Darkness Survey tem 300 milhões de galáxias. A diferença é que eles medem o espectro de cada galáxia. Nós medimos só essas fotografias. Então, a nossa precisão é muito menor. Por isso que eles podem fazer um mapa tridimensional. Mas nós não conseguimos fazer um mapa tridimensional. A gente consegue fazer essa análise tomográfica, que a gente chama, em fatias, 5 fatias de redshift. É o que a gente faz. Mas só para completar, posso fazer pegar mais uma coisa aqui? Só para você ver uma outra simulação, Júlia, que eu acho bem mais simples. Assim. Essas simulações são ótimas. É mais fácil de ver isso daqui. Aqui é uma simulação só de matéria escura, não tem baryons. Eu podia mostrar a simulação, porque eu tenho um filme em algum lugar também, mas não quero fazer o download agora. Mas aqui tem umas snapshots dessa simulação. Você começa com algo super homogêneo, com redshift 27, e vai evoluindo só com a gravitação. E você começa a ver surgir essas estruturas aqui, tá vendo? É uma coisa, isso que a gente chama de estruturas. Se isso estava te incomodando, era isso que a gente chama de estruturas, tá?
Sim, eu acho que e aquela imagem que você mostrou do redshift também ajuda bastante, eu acho que me deu uma dimensão melhor de como que mede isso, como que a gente pode ver, né, e como isso mostra pra gente, né. Eu entendo que eu acho que o que me confunde um pouco é essa questão da simulação artística, sei lá, talvez, com o que a gente está medindo, talvez, mas eu não tenho certeza.
Então, primeiro, os dados do EBOS não eram artísticos, aquilo eram realmente dados reais. E essa simulação também não é artística, é uma simulação...
Sim.
Então, aqui não tem nada artístico. E o interessante é que, só pegando bolas newtonianas, né? Aqui tem, não sei quantas bolas tem ele deve falar.
É que também, às vezes, eu vejo vídeos, né, sobre o assunto, para tentar entender um pouquinho o básico. Mas, às vezes, a gente não checa com ninguém e aí a gente cai num erro, sabe?
Sim, claro. Mas dá uma olhada nessas simulações aqui, que são super legais. Faz o download dos vídeos aqui.
Claro.
E aqui são bem simples, são simulações só com matéria escura. Não tem... O que eu digo é que quando você inclui átomos, as simulações são muito mais complexas, porque você tem que levar em consideração os processos atômicos. Por exemplo, a perda de energia por emissão de radiação. Que você não tem considerado no caso da matéria escura só. E é super legal também, porque tem simulações que você pode pôr mais ou menos energia escura. E se você põe mais energia escura, por exemplo, você inibe a formação de estruturas. Então, é muito legal ver isso acontecer.
Nossa, eu não fazia ideia. Entendi.
Mas, enfim, dá uma olhada. Tem muita coisa legal para se fazer. Pra ver.
Claro, muito obrigada.
Bom, eu queria agradecer muito ao professor Rogério por ter comparecido aqui. A gente vai fazer... Bom, calma, deixa eu parar de gravar nesse exato momento.